Every year, the Earth grows a little hotter. Ice is melting. Forests are burning. Storms are more intense, and summers are stretching longer than ever. All of it is telling us, it's time to change. But what if the solution doesn't lie in reducing, but in replacing altogether? What if there were a form of energy that's clean, powerful, and sustainable, capable of powering the entire planet without leaving a trace? Tonight, we're talking about the energy of the future. A beacon of hope, or just a distant illusion? Now, dim the lights, relax, and let go. We're about to explore the technologies shaping what's to come, from clean nuclear energy to fusion, and even power harvested from space. So join me now, as we begin the journey, to find the kind of energy that could change everything. The Earth, the blue planet we call home, has existed for billions of years, far longer than any creature that has ever walked its surface. We, the self-proclaimed masters of this world, have inhabited it for a mere 2.8 million years. That is not even a fraction compared to the dinosaurs, who reigned for over 100 million years, and then vanished. So what was their fate? It's not hard to imagine. Humanity is only one among countless species that have lived on Earth. In some distant future, even if we disappear, the planet will persist, circling the sun. Everything we have, everything we are, and everything we ever will be originates from this world. So what happens if we deliberately destroy it? Whether we like it or not, the reality is that our climate is changing. Winters once expected in Q4 now arrive months late. Summer 2023 was recorded as the hottest in over 200 years. Temperatures in major cities have soared above 40 degrees Celsius, and this isn't isolated, it's happening worldwide. Even more alarming, every time we set a new temperature record, a new one is broken several years later. The second hottest summer in history was in 2016, that's just a few years ago. At this rate, outdoor temperatures will soon reach levels that make breathing outside nearly impossible. Speaking of breathing, the air is changing too. In 2022, IQ Air reported that China, India, and Pakistan were home to the world's most polluted cities. In 2021, images of Beijing's yellowish haze at midday filled headlines. It wasn't fog, it was smog and dust. And this isn't unique to China. It happens elsewhere, and Vietnam is no exception. Since 2019, photochemical smog phenomena have emerged in vibrant Saigon, and Hanoi is suffering similarly. Pollution indices regularly breach healthy limits, triggering stronger measures in respiratory health care. But environmental welfare goes even deeper, and we haven't even touched on the increasingly erratic natural disasters. According to the United Nations, from 2000 to 2019 humanity endured 7,348 major natural disasters, causing 1.2 million deaths and costing the world $2.97 trillion. That is nearly triple the cost in the previous 20 years, from 1980 to 1999, when 4,212 disasters cost $1.6 trillion. Heavy downpours have surged in recent years, resulting in floods and landslides across the world. At the end of 2023, CNBC reported that in just the first 11 days of September, 8 severe floods hit 4 continents: central Greece, northwest Turkey, southern Brazil, Spain's central and coastal regions, southern China, Hong Kong, and the southwestern U.S. These floods will continue, bringing serious consequences for human lives and economies, such as crop losses and threats to food security. Storms, too, are becoming increasingly damaging. In the Pacific typhoon season of 2008, there were 22 storms with 11 categorized as super typhoons, the strongest being Jangmi with winds of 215 km per hour. 10 years later, in 2018, there were 29 storms, including 2 extreme ones, Yutu and Kanra, reaching 255 km per hour. Clearly, both the number and intensity of storms have risen. The toll on human lives and economies keeps climbing, imposing heavy regional burdens across Southeast Asia. Air quality, rising temperatures, habitat changes, and powerful storms, none of these are issues humans can solve overnight. In fact, sometimes we have very little control, especially when it comes to events in the sky. Everything that has happened, and is still happening, is actually caused by us. The climate is changing, and no matter how much people deny it, we remain one of the most significant drivers. Has today's situation evolved? The answer is, indeed, it has. Global air is now more polluted, urbanization is accelerating, and with it comes countless sources of pollution, from construction projects, vehicles, to factories built to support that growth. Between 1941 and 1954, global energy primarily powered manufacturing plants. But after the Soviet Union's collapse and the dawn of the digital age, energy demands shifted to major cities to support daily living. Basic appliances like electric fans, induction stoves, even personal computers now consume energy at alarming levels. In 1990, global electricity usage was below 400 exajoules. Today, it has surpassed 500 exajoules. We're using more energy than ever before. Consequently, power plants mushroom to meet that demand, but here lies the critical point: energy cannot be created or destroyed. So, where does that energy come from? In short, from within the earth. We extract natural resources, bring them above ground, and burn them to generate steam that turns turbines, transmitting electricity through power lines. This process, from extraction to combustion, produces countless waste gases, chiefly CO2. And that's where the problem begins. Sunlight sustains life on Earth by providing the right temperature for liquid water, warm enough to prevent freezing, yet not so hot as to boil it away. Essentially, we reside in a perfect zone for life, neither too hot nor too cold. But sunlight is energy, and when it reaches Earth, some is absorbed by the atmosphere and ground, while the rest is reflected back into space, especially by light-colored surfaces like ice. A delicate balance between absorbed and reflected energy sustains life as we know it. A slight shift in this balance could spell disaster. Earth's orbit isn't always a perfect circle. Sometimes gravitational forces from other massive planets distort it, causing our planet to move farther from the Sun. This isn't permanent, it cycles roughly every 22,000 years. Every 22,000 years, Earth enters a glacial period. So where are we now in that cycle? Honestly, as long as the polar ice caps still exist, we are still in an ice age cycle. Specifically, this current ice age began 3 million years ago, and we are now living in the warmest phase of that glaciation. It sounds unbelievable, doesn't it? But it's true, we are still in an ice age. While the poles should be locked in perpetual ice, we are already enduring summers where surface temperatures exceed 40 degrees Celsius. This paradox is the essence of climate change. Yes, Earth naturally cycles between warm and cold periods, but not at this terrifying speed. Surface temperatures have increased by about 0.08 degrees Celsius per decade since 1880. But since 1981, that rate has nearly doubled to 0.18 degrees Celsius per decade. At this pace, 2022 became the 6th hottest year on record, and alarmingly, the 10 hottest years have all occurred since 2010, with 2023 breaking those records again. July alone shattered previous heat records. Why is Earth heating so abruptly? Because we are a unique species. We lack sharp claws, immense muscles, flight, or finned bodies, but compensate with thinking and social organization, much like wolves. Though individually weak, collectively we are powerful. That capacity for connectivity and communication, not just warning calls but stories and beliefs, is what drove us out of caves and into new environments. Despite the comfort of caves, humans chose to build shelters from earth and leaves just to live together. Our storytelling and beliefs pushed us forward, powered our use of energy, and in the process, unbalanced the fragile equilibrium that sustains life. Humanity's greatest achievement in ancient times was mastering agriculture, water management, and cultivation. Thanks to rice cultivation, people controlled their food supply, accumulated surplus, and traded. With abundant food, humans domesticated wild animals, turning them into allies in the struggle for survival. But this was a turning point. Just as humans no longer needed fangs or claws to hunt, we no longer needed nature to survive. We created our own environment. Building civilizations required clearing forests, leveling mountains, and destroying ecosystems. Soon, wild forests turned into vast farmlands, and birds' nests into bare land ready for planting. As agriculture developed and yields grew, humans gained security and began to explore deeper concepts like community and empathy. Instead of spending days gathering berries, people could farm for a few hours and return home to enjoy leisure. Stable living conditions gave humans time to create tools for entertainment, pleasure, and, unfortunately, decadence. We lived longer, eating better and sleeping soundly, but we also became greedier, hungrier. Conflicts over status, land, and wealth erupted. We drifted apart, building kingdoms of our own on land once inhabited only by wild creatures. From nomadic tribes sprouted cities. From groups who left home, new worlds emerged. In a few thousand years, humans had claimed the entire globe. But a few hills or forests cannot change the climate. The environment needs time, and time is the key factor. Over time, as social welfare and nutrition improved, humans began to live longer. Families no longer had to bear many children because individual productivity was higher, and children were educated rather than sent to work. People grew smarter, stronger, more creative. By the late 16th to early 17th centuries, the concept of science emerged and flourished. In the 18th and early 19th centuries, a new era dawned. Humans discovered how to run the world without manual labor. They created machines, colossal engines that replaced hundreds or even thousands of workers. Production increased hundreds of times. But to clothe and feed ourselves, we destroyed the environment, mining ores, digging coal, burning oil to power machinery. Money became everything, and the Industrial Revolution turned the wealthy into the ultra-rich. Yet that wasn't enough, they wanted more. The invention of electricity pushed civilization further. By 1882, when electricity became widespread, humans rapidly expanded roads, reclaimed continents, and extended territories. Power plants sprouted everywhere, spewing tons of CO2 into the air without concern. Then came 2 world wars. Science and technology reached new heights. Minds worked tirelessly to create the deadliest machines imaginable. When the wars ended, the wounds were deep, but they also became a catalyst to fight the past. We emerged from the wars like triumphant losers, exhausted yet determined to rebuild. But our efforts severely harmed the environment. To restore roads, we laid asphalt, which itself is a product of a highly toxic process. To build infrastructure, we produced cement, also a waste-intensive endeavor. To power cities reborn, we built more power plants. Burning coal continued to pollute the atmosphere. Then came transportation, cars, motorbikes, airplanes, machines that emit thousands of tons of CO2 daily, pushing Earth to the brink of fever. In just 50 years, from 1950 to the present, energy consumption has multiplied 5-fold. And this is just the beginning. Social welfare improved significantly thanks to medical and pharmaceutical research. Lifespans increased, children were born in numbers, and elders lived longer. The global population hit 2 billion in 1927. Less than a century later, that number tripled to 6 billion by 1999. Within just one decade, we added another billion, and in the early 2020s, we reached 8 billion. Population growth means higher welfare demands, leading to more resource extraction and more pollution. Yet that's not the biggest problem. To feed billions of hungry mouths born each day, the world has drained the land to grow crops, not just for direct consumption, but also for dairy, fabric, and meat. This has led to two unforeseen consequences. The first consequence is the acceleration of deforestation in recent years. Humanity's expansion has ravaged temperate forests in Europe from the 18th to the 20th century. By the early 20th century, this tree-clearing disease reached Asia to support its rapidly growing population. Ancient forests were replaced by cities and farmland. Between 1950 and 1979, humanity felled 320 million hectares of tropical forest and 20 million hectares of temperate forest. From the 1980s into the early 21st century, we cut another 220 million hectares of tropical forest and 5 million hectares of temperate forest. The loss of forests not only causes floods, erosion, and soil degradation, but also destroys our only natural mechanism for sequestering CO2, photosynthesis in plants. Trees absorb CO2 and transform it into organic material, such as leaves and fruit. When trees die, the carbon they've absorbed is locked in the soil or transferred to living organisms. Trees also generate oxygen, which all breathing life depends on. But on the global CO2 battleground, CO2 is winning. Our only natural CO2 sinks, trees and ocean algae, are outmatched by factories, power plants, and oil fields that belch CO2 through smokestacks. Just oil fields alone emit an estimated 6.3 billion tons of CO2 annually. And that's not all. Life itself produces CO2, oceans outgas 90 billion tons per year, and plants and animals another 121 billion tons. What matters most, however, is our oxygen supply. While people often call forests Earth's lungs, most oxygen comes from the oceans. Rising atmospheric CO2 is absorbed by seawater, increasing acidity, damaging marine ecosystems, and threatening the oxygen we breathe. With escalating deforestation and relentless urbanization, the balance between nature and humans is collapsing. As a result, atmospheric CO2 increases by about 10 billion tons each year. In short, we're destroying the very trees that help us breathe. But this is only the first consequence. Clearing forests to plant crops doesn't have to be a zero-sum game. Humans could farm land sustainably, but this isn't happening everywhere. In many developing countries with weak economies, uncontrolled deforestation is rampant. Forests are cleared to plant crops on degraded land, irrigated improperly, and overgrazed. These practices degrade ecosystems, ultimately turning fertile land into desert. Once forests that retain moisture through shade and transpiration are removed, the land dries out and gradually desertifies, like a spreading cancer. As farmland becomes barren, people clear more forested land, even as cultivable land shrinks. The economy suffers, yet ironically, the greatest casualties are humans themselves, as desertification devastates livelihoods and communities dependent on the land. However, that is only a small part of the larger picture. You could see this as a chicken and egg dilemma. We seek to improve our quality of life, but in doing so we make the environment pay a heavy price. Now that the environment is suffering, we are forced to improve our living conditions again to adapt. And so the cycle continues, while atmospheric CO2 keeps rising, and from there the pace of global warming begins to spiral. To put it poetically, we have created a monster that we ourselves cannot restrain. Light is a particularly elusive concept. We once thought light was purely particulate, until we discovered it was also wave-like. Essentially, light is a form of energy wave with particle-like properties, and to this day experts are still investigating whether it is a particle or a wave. Whatever it may be, light carries energy, and energy cannot be created or destroyed. So what about sunlight? Sunlight is not just white light. It contains multiple wavelengths of energy that the human eye cannot perceive. When this light enters Earth's atmosphere, it collides with gas molecules and triggers strange reactions. Molecules with symmetric electric structures, like ozone, allow light to pass through unaffected. However, molecules such as CO2 and methane, those that can trap infrared waves, i.e. heat, behave differently. This is precisely the mechanism by which greenhouse gases heat our planet. With greenhouse gas concentrations continually rising, the effects of Earth heating up become clearer. Polar ice begins to melt and flow into the oceans, directly altering ecosystems. Ice reflects sunlight back into space, helping to keep Earth cool. As the ice melts, sunlight hits the ground directly, heating the planet further and accelerating more melting. Rising temperatures also warm the oceans, which absorb more CO2, warming sediment layers and releasing greenhouse gases sealed for millennia. Thus the cycle repeats: Earth heats, ice melts, CO2 rises, and it heats again, until eventually even permafrost releases toxic gases that further accelerate warming. Meanwhile, trees are cut to clear land for urban or agricultural expansion, reducing the vegetation's capacity to absorb CO2. Atmospheric CO2 accumulates, and the planet warms further. Melting ice causes sea levels to rise, turning coastal areas into new shorelines, homes of millions transformed into open water. Between 1880 and 2013, sea levels rose by an average of 23 centimeters, and with current warming trends, that number will continue to climb. But, moving inland is not our only consequence. Earth's climate is governed by pressure systems and ocean currents, and when these patterns are disrupted by rising temperatures, weather extremes follow. Climate change creates paradoxes. We now suffer more intense droughts alongside stronger floods and storms. Droughts in places like Australia and Brazil create ideal conditions for wildfires, which release even more CO2. On the other hand, heavy rains in Southeast Asia and Africa flood farmland and disrupt livelihoods. Tropical cyclones are becoming more frequent and powerful as ocean temperatures rise. In the first decade of the 21st century, the strongest storms in history devastated communities, causing hundreds of thousands of deaths and massive economic loss. The aftermath is homelessness, food shortages, and conflict over scarce resources after catastrophic weather events. Our world has never been this extreme, and perhaps this will be the last moment in human history when we witness it. Because if there is a second round, we likely will no longer exist to see it. These weather extremes aren't separate from climate change, they are climate change. If humanity doesn't wake up and unite to save ourselves, we may soon be only a faint footnote in Earth's history. As our societies grow, we consume more energy for factories and cities. We burn fossil fuels to power turbines and generate electricity, yet this process pushes Earth toward dangerous levels of warming. So, when will humanity stop burning these fuels? When we talk about burning for electricity, we must mention the 2 degrees Celsius limit, the global temperature increase threshold beyond which humanity might self-destruct. In other words, if we continue emitting CO2 and escalating the greenhouse effect, Earth will warm by 2 degrees Celsius, and at that threshold, we will suffer the greatest consequences. The United Nations set this 2 degrees Celsius limit at the 1992 Earth Summit as a critical boundary to guide human intervention in our fate. Following that decision, governments began requiring global emitters to drastically reduce CO2 output before we hit that 2 degrees Celsius danger line. From this, the concept of a carbon budget emerged. The carbon budget is the global limit on CO2 emissions to keep warming under 2 degrees Celsius. Estimates say we can release about 870 GTC, gigatons of carbon. However, since 1870, humanity has already burned enough fuel to emit 545 GTC, leaving only 325 GTC left in the budget. With such a limited budget, countries must find alternative energy solutions to fossil fuels to ensure their future. The global carbon budget is divided into phases where emissions gradually decline as we switch to green energy, ensuring humanity survives past 2100. To reduce CO2 emissions, we can start with simple steps: improve energy efficiency, eliminate wasteful appliances, use LED lighting, and replace high-energy pumps and devices. We can also switch to low-carbon fuels like biofuels or biogas for daily use. Reforestation remains a vital mission to restore Earth's natural CO2 filters after 2 centuries of merciless deforestation. However, all the above methods only help to soften the steep slope of carbon escalation. The biggest issue still lies with massive thermal power plants that burn hundreds of thousands of tons of fossil fuels every day. But without electricity, we cannot live, so how should we deal with these power plants? The concept of green energy has been mentioned in the media since the early 21st century. We are becoming increasingly aware of our impact on the planet, and movements since 2009 have urged the world to shift toward more sensible energy sources. However, green energy did not first emerge in the 21st century. In fact, it dates back to the 18th century. In 1771, Richard Arkwright, a British inventor, created the first water-powered engine, kickstarting the Industrial Revolution. By 1878, the first hydroelectric project was launched in Craigside, England, by William Armstrong. Just a few years later, in 1882, the first hydroelectric power plant was officially operational, and that same year, the first thermal power plant was also constructed by Thomas Edison. In 1883, Carl Fritz successfully developed the first solar panel, and only 4 years later, Scottish professor James Blyth created the first wind energy system. Clearly, humans discovered clean energy sources early in modern history. However, due to the rapid pace of urbanization, water and wind were not enough to meet growing electricity demands. After years of experimentation, only thermal power could keep up. But does this mean humanity intentionally chose thermal energy to destroy the planet? No, it was an inevitable consequence of development. Every form of progress has its dark side. But that does not mean we should let thermal power dominate the Earth. Thermal power depends on mineral resources, and resources are not infinite. Once coal runs out, thermal power will no longer be viable. In fact, humanity could go extinct before we even finish burning all fossil fuels. So can green energy sources truly replace and keep pace with humanity's expansion? The answer is, only with serious investment. Although green energy was discovered as early as the 18th century, it wasn't until the 21st that humans began developing it in earnest. In 1998, Iceland became the first country to announce a 100% green energy goal. By 2003, Japan followed with a similar commitment, and in 2011, Australia joined the movement. The pursuit of green energy isn't just about pioneering a new energy industry, it's about securing a livable future for the planet. Why do countries keep announcing green energy transitions? Because humanity has relied on fossil fuels for so long that switching directions is extremely difficult. And the profits from the oil industry are far too large to give up easily. Transitioning to green energy means cutting into the interests of oil corporations, so doing this requires strong policy support. However, this isn't the only barrier. Suppose a country wants to develop wind energy, it would need vast plains, open grasslands, or large maritime zones to install wind turbines. If the country lacks open land, there are almost no options left. Some popular alternatives include hydropower, nuclear power, and solar power. Yet, these are not perfect choices either. First, unlike giant thermal power boilers or hydroelectric dams, wind power can grow like trees anywhere, but it requires enormous space. To build a wind farm, we must plant massive windmills across wide plains or offshore to harness enough wind to turn the blades. Constructing these giant iron pinwheels is extremely costly and can even emit CO2 into the environment at levels comparable to building a thermal plant. But the issues don't end there. These giant wind turbines not only take up large areas of land but also hinder the development of nearby urban infrastructure. That means, wherever wind power exists, urban activity is somewhat restricted. Moreover, wind farms can also impact their surrounding environment by generating noise and posing a danger to birds, bats, and other winged creatures flying through the area. However, all those measures only make the carbon climb less steep. The biggest problem remains the massive thermal power plants burning hundreds of thousands of tons of fossil fuel every day. But without electricity, we cannot live, so what should we do with these plants? The concept of green energy has appeared in the media since the early 21st century. We have become increasingly aware of our impact on the planet, and since 2009 movements have pushed for a shift to more sustainable energy sources. However, green energy isn't new to this century. In fact, clean energy dates back to the 18th century. In 1771, Richard Arkwright created the first water engine, kickstarting the Industrial Revolution. By 1878, the first hydroelectric project was built in Craigside, England by William Armstrong. A few years later, in 1882, the first hydroelectric power station began operation, and in the same year, Thomas Edison built the first thermal power plant. In 1883, Carl Fritz made the first solar cell, and just 4 years later Scottish professor James Blyth generated electricity from wind. These clean energy sources were discovered early in modern history, but rapid urbanization and energy demand meant water and wind power couldn't keep up, so thermal power became dominant. Is humanity to blame for choosing thermal power and destroying the planet? No, it was an inevitable consequence of development. Every advancement has a downside. But this doesn't mean we must resign ourselves to thermal power's dominance. Thermal plants depend on finite fossil resources. Once coal and oil run out, thermal power will collapse, possibly before humans face extinction. Can green energy replace fossil fuels? Yes, but only with serious investment. Though renewable energy existed since the 18th century, only in the 21st century have we actively pursued it. In 1998, Iceland became the first country targeting 100% green energy. Japan followed in 2003, and Australia in 2011. The push for clean energy isn't just innovation, it's survival. Governments are pivoting because the fossil fuel economy is entrenched and profitable, transitioning threatens vested interests, so bold policies are essential. Yet geography complicates matters. A country with limited space may struggle to deploy wind farms or solar fields. Alternatives like hydro, nuclear, or offshore wind come with their own challenges. Wind power can be installed almost anywhere, but requires huge land or sea tracts. Building wind farms is costly and emits CO2. Plus turbines can interfere with urban development, generate noise, and threaten birds and bats. Even ignoring life cycle emissions, wind energy contributes only about 5% of global power replacement for thermal plants. As Thanos said, the cost is everything. Turbines eventually wear out, and their blades, made of carbon or fiberglass, are hard to recycle. Disposal options rely on landfilling or pyrolysis, which itself burns fossil fuels. In short, wind isn't a panacea, and solar is similar. Solar power costs have dropped since 1990, but large surface area is still needed. Efficiency peaks only under sunlight, unlike 24/7 wind. Manufacturing solar panels requires energy-intensive processes, heavy use of fossil fuels to purify silica and combine it with toxic chemicals like cadmium, antimony, arsenic, and lithium. The result, panels last 20 to 30 years before needing strict disposal. Solar graveyards will grow unless future generations develop better recycling. For now, both wind and solar, production to disposal, consume fossil fuels and generate emissions. So, is there a better option? Yes, nuclear energy. Since the invention of the atomic bomb, nuclear energy has been envisioned for electricity generation. The principle is simple: control a fission reaction, unlike in bombs, and channel the heat into electricity. If this sounds basic and similar to thermal power, why hasn't nuclear been adopted as widely as wind or solar? Because scale matters. As societies grow, energy demand skyrockets, and that demand has ravaged our environment. Climate change is no longer a theory, it's happening now, affecting every household. So what can slow it? Since the early 20th century, we have unlocked the structure of matter. Visionaries like Einstein showed that mass and energy are interchangeable. If we can harness heavy particles and split them, immense energy is unleashed. It sounds abstract, but it's happening all around us. Combustion transforms matter into heat and light, our cells convert matter into energy to sustain life. The real breakthrough is understanding and controlling this process, and deploying it efficiently. From here, let us look up at the stars. They operate based on two mechanisms: nuclear fusion and gravity. The immense gravity in their cores compresses hydrogen atoms together, triggering fusion reactions that form helium and release energy in the form of light and electrons. That is the very source of the light we see from the sun every day. The mechanism of fusion in stars closely resembles the principle behind nuclear energy. Humanity first approached this during World War II, when the greatest minds of the era gathered in Los Alamos, USA, to develop the first nuclear weapons. Oppenheimer was not the first to imagine colliding atomic nuclei, but he was the first to make it a reality. The result was atomic bombs that formed towering mushroom clouds, an iconic symbol of 20th century destruction. Instead of fusing nuclei like in stars, nuclear bombs use fission, splitting heavy nuclei like uranium to release neutrons. These neutrons then collide with other nuclei in a chain reaction, releasing exponential amounts of energy. The consequences of this, we already know. After the war, scientists no longer wanted nuclear energy to be solely a weapon. While political leaders scrambled in the arms race, scientists began asking, if nuclear reactions can produce such vast energy, can we harness it for life? The answer was yes. And in fact, the idea was proposed as early as the 1930s. The concept of splitting atoms to generate energy was suggested by Enrico Fermi, and in 1942, he and his team created the first artificial nuclear chain reaction. However, due to war and politics, Fermi's work received little attention. It wasn't until the 1950s that he continued experiments and built the first nuclear power plant in Idaho, 1951. By 1957, the first commercial nuclear plant began operating in Shippingport, Pennsylvania. At this point, humanity had a solution: extract energy from the atom, the very building block of matter. But this was still the early stage of nuclear technology. The first challenge was safety. One small mistake could obliterate an entire area. In addition, construction and operation costs were extremely high, since the technology was new and required expert supervision. It was not just an industrial accident, it was a historical scar on nuclear energy. In 2011, the Fukushima disaster in Japan rang yet another alarm. A 9.0 magnitude earthquake triggered a tsunami that destroyed the plant's cooling system, causing core meltdown and radioactive leaks into the sea. When nature unleashes its fury, even the most advanced technology can collapse. From these two major incidents, the question arises, is nuclear energy truly a long-term solution? The answer is yes, but not in its old form. Today, humanity is developing new generation reactors, smaller, safer, and easier to control. For example, molten salt reactors, MSRs, and small modular reactors, SMRs, are designed to shut down automatically if overheating occurs, avoiding the explosion risks seen at Chernobyl. Moreover, the world is chasing an even greater dream, fusion, not fission, as is currently used. If successful, fusion could provide nearly limitless energy, with no radioactive waste, no risk of explosion, and it would mimic the very way stars burn. The ITER project in France is proof of this vision, with more than 35 countries joining hands to develop a so-called artificial sun. However, reaching that day still requires time, a great deal of time. And for now, with energy demands constantly rising, nations must choose, either continue relying on fossil fuels and sacrifice the environment, or take the risk with nuclear power, but control it better than ever before. We don't have a perfect option. Solar power is unstable and emits pollutants during production. Wind energy takes up large areas and generates difficult-to-manage waste. Nuclear power carries major risks if accidents occur. Thermal power emits enormous amounts of greenhouse gases. And that's the paradox of the 21st century. We need electricity to live, but the more electricity we use, the closer we push ourselves toward extinction. In short, to move forward, humanity needs more than just new technology. We need new thinking. It must begin with how we consume electricity, how we produce it, and especially the awareness that no energy source is truly 100% clean. The question is no longer, which energy source causes the least harm, but rather, are we willing to sacrifice today's convenience to survive tomorrow? For that reason, if we fail to pump enough water to cool nuclear reactor cores and harness steam, we risk reactor depletion, resulting in what's called a nuclear meltdown. The consequences of a meltdown are perhaps best understood through the tragedies of Chernobyl and Fukushima. From what happened in those places, it's clear why the public fears nuclear energy so deeply. Fundamentally, to ensure sufficient cooling water for nuclear plants, we must build them near water sources. But building reactors near lakes and rivers is like setting a timer on a bomb that could threaten not just people near the plant but also every location downstream if disaster strikes. Following past nuclear incidents, protests have erupted to demand governments halt further construction of nuclear power plants. In essence, the development of nuclear energy began to decline as the 21st century arrived. However, protests were not the main reason for nuclear power's decline. The lingering fear of a destructive arms race, with facilities developing weapons of mass destruction under the guise of power plants, shook the world in the late 20th century. This led to ruthless, inhumane hunts during the early 21st century. Because of this, fear surrounding nuclear energy hasn't diminished, it's only grown. Even though sanctions have been imposed on countries suspected of developing weapons of mass destruction since the early 2010s, continued nuclear development and recurring talk of nuclear war have only hindered the pursuit of clean energy. The threat escalates. Mass media constantly labels nuclear energy as dangerous. And whenever nuclear power is mentioned, we immediately think of catastrophes, while few realize that most of those events happened in the mid-20th century. Why the mid-century? Didn't Fukushima happen in 2011? That's true. But Fukushima and other major nuclear disasters all share one thing in common: they were built with nuclear technology from the 1950s and 60s. In other words, they were outdated and especially hazardous machines. These plants weren't just constructed with old technology, they were also extremely costly, making them impractical as a global primary power source. So despite nearly a century of developing nuclear power, it still accounts for only 10% of the world's total energy. Looking at that figure, many people believe nuclear energy isn't worth pursuing. Expensive, dangerous, contributing only 10%, while solar and wind power seem more stable and safer. So why choose nuclear? Because we're not looking at the full picture. Like nuclear power, wind and solar also have strengths and weaknesses. However, when it comes to durability and adaptability for the future, the performance of nuclear power simply can't be compared to the other two. Because nuclear power clearly outperforms wind and solar energy. Wind and solar energy are entirely dependent on nature to generate electricity. On bright, breezy days, there's little to worry about. But if a stormy season interrupts solar power, or if wind turbines require maintenance, the story becomes completely different. The issue with electricity isn't about how we generate it, but whether we can sustain it consistently. A city cannot function if the power supply is unreliable. Therefore, the durability and continuity of the power flow must be absolutely guaranteed. At present, wind and solar energy still lack an effective solution to this issue. Furthermore, we have yet to address the logistical challenges of these two sources. Wind and solar farms must be built on vast, open lands to maximize energy output. This means we need incredibly complex underground power grids to transmit electricity from these remote areas back to urban centers. These power lines often become a major barrier to the development of wind and solar stations because the installation, maintenance, and expansion processes directly affect the surrounding environment. No one wants to cut through an entire mountain just to thread power lines from a distant sea to the city, or to hunt down a fault in the forest whenever the power flickers. While these two renewable sources are still struggling to address such issues, nuclear power faces none of them. For this reason, if we don't pump enough water to cool the nuclear core and harvest steam, the reactor will overheat, leading to what we call a nuclear meltdown. The consequences of a meltdown are all too clear. Just look at Chernobyl and Fukushima. From what happened in those two places, we can understand why the public is so afraid of nuclear energy. Fundamentally, in order to supply sufficient water to nuclear power plants, they must be built near water sources. But building next to rivers and lakes is like setting a time bomb, threatening not only the people living around the plant but also all areas downstream if disaster strikes. After the aforementioned nuclear incidents, many protests erupted to stop governments from building more nuclear plants. In essence, the development of nuclear energy has shown signs of decline since the beginning of the 21st century. However, the protests themselves aren't the main reason nuclear plants are fading. Widespread concern over a potentially destructive arms race, with facilities developing weapons of mass destruction disguised as power plants, shook the world in the late 20th century. This led to ruthless and inhumane purges in the early 21st century. For that reason, fear surrounding nuclear power hasn't diminished, it has only spread further. Although sanctions against countries suspected of developing weapons of mass destruction were issued in the early 2010s, the fact that nuclear development continued and the recurring threat of nuclear war was repeatedly mentioned did nothing to help the pursuit of clean energy. The danger continues to escalate. Mass media consistently labels nuclear power as dangerous, and whenever nuclear energy is brought up, people immediately think of disasters, while almost no one realizes that most of these events happened in the mid-20th century. Why the mid-century? Didn't the Fukushima disaster happen in 2011? That's correct. But Fukushima and other nuclear catastrophes all share a common factor: they used nuclear plant technology from the 1950s and 60s. In other words, they were outdated and particularly hazardous machines. These nuclear plants weren't only built with old technology, they were also extremely expensive, making them unlikely to become the main energy source for the world. So even though we've had nearly a century to develop nuclear power, it still only accounts for 10% of the world's total energy. Seeing that number, many believe nuclear energy isn't worth pursuing, expensive, dangerous, and contributing only 10%, while solar and wind energy appear far more stable and safer. So why choose nuclear? Because we're not looking at the full picture. Like nuclear power, solar and wind energy each have strengths and weaknesses. However, when it comes to longevity and adaptability for the future, there's simply no comparing the performance of nuclear power to the other two. The reason is that we're not looking at the big picture. Like nuclear energy, wind and solar both have strengths and weaknesses. Yet when it comes to durability and future adaptability, nuclear power simply outperforms the other two. Because nuclear energy absolutely beats wind and solar. Wind and solar depend entirely on nature to generate electricity. On fine, windy days there's little to worry about, but if a storm disrupts solar output, or if a wind turbine needs maintenance, the situation changes completely. The real issue isn't how we generate electricity, but whether we can sustain it reliably. A city can't function if the power keeps flickering on and off. We must guarantee a consistent, uninterrupted power supply. At present, wind and solar haven't solved this effectively. Moreover, logistical challenges remain. Wind and solar farms require vast open land to optimize energy production. Transmitting that power to cities demands complex underground grid networks, often a major obstacle. No one wants to carve through a mountain to run cables from an offshore farm or trek into a forest every time there's a power glitch. While wind and solar still struggle with these issues, nuclear power faces none of them. Its generation isn't weather-dependent, and new generation reactors can be built almost anywhere. Logistical constraints are minimal. Old nuclear plants required proximity to rivers and lakes, but that's old technology. New plants can be safely located inland, or even within cities, optimizing power use. Why is this feasible? Aren't nuclear plants massive smokestacks with dangerous, uncontrollable radioactive waste? Not necessarily, because that's not the case with next-gen nuclear, which centers on a material named after the Norse god of thunder, Thor. Thorium is a light radioactive metal discovered in 1828 by Swedish chemist J.J. Berzelius. It's abundant, 3 times more than uranium, and exists in nature as non-soluble thorium-232, with a decay rate slower than 3 times Earth's age. Under special conditions, thorium turns into thorium oxide, a heat-resistant material once used in light bulb filaments and heat transfer equipment. But that's not why it matters today. Thorium was considered as reactor fuel during the development of the atomic bomb, but overlooked because it isn't self-fissionable like uranium. That actually makes it ideal now. Thorium can be enriched to transmute into uranium-233, a fissile fuel. In molten salt reactors, MSRs, we use a liquid thorium-based fuel that decays into protactinium, then uranium, which sustains the reaction, converting energy. The fuel remains liquid and can be removed mid-operation, preventing meltdowns. Because thorium itself can't sustain a chain reaction, reactors can shut down instantly by removing the uranium stimulus. Reactors run cooler and more efficiently than uranium ones, generating far less waste, much of which can be recycled back into the fuel cycle, eliminating long-term storage needs. Thorium's advantages: high abundance, incredible safety, high efficiency, and minimal waste. That's why thorium reactors are being built now. For instance, China broke ground on their first thorium reactor in Wuhan in 2018. In summary, humanity has triggered a global temperature race with climate change, but lacks an effective brake. We must reduce greenhouse gases. Wind and solar help, but aren't optimal. Nuclear energy, especially thorium reactors, could be our new hope. Past disasters like Chernobyl or Fukushima reflect outdated technology and poor management, not fundamental flaws. If we want to return CO2 to safe levels, nuclear must play a central role. Thorium offers safe, efficient, clean power for a future where everyone uses green energy to protect themselves. But we need governments to re-evaluate nuclear energy. The blurred line between power plants and weapon programs must be removed. We can't adopt thorium on a global scale without political trust. Until then, we wait. That's the full story of future energy sources. We're still improving life while searching for a better alternative to fossil fuels. Given recent decades, perhaps it's time humanity reconsider nuclear power, and give it a real chance to develop. If you enjoyed this video, please like, subscribe, and ring the bell so you won't miss our future content. Thanks for listening, and see you next time.